Dear colleagues, my name is Nađa Gavrilović and I'm with the Department of Computer Science at University of Niš, Faculty of Electronic Engineering. The topic of my today's presentation is design and evaluation of proof-of-work-based anti-spam solution. This paper is joint work of me and my colleague Vladimir Ciric, who is also with the Department of Computer Science at the same faculty. I will start my today's presentation with the paper motivation. I will briefly discuss the paper background, which includes SMTP protocol and proof-of-work concept. Furthermore, I will present design and implementation of an anti-spam solution based on a novel proof-of-work concept, and I will conclude with evaluation of the implemented system during the distributed spam attempt. According to a report from March this year, there is 306 billion of globally sent email messages in a single day. Approximately 50% of the total traffic is spam, according to the same report. Spam represents the abuse of electronic systems and the SMTP protocol for the purpose of sending mass unwanted messages. Those messages most often contain advertising content, but they can also contain various attacks at users' data and users' identity. The main feature of spam, which makes it easy to use and widespread, is that it is almost completely free. The initial idea of pricing for every access to a shared protected resource induced development of today's proof-of-work systems. So the goal of this paper is to design an anti-spam solution based on a novel proof-of-work concept and to evaluate the server load during a distributed spam attempt. The implementation of such a system requires an SMTP protocol extension, which will be presented. SMTP protocol defines rules for sending and reliable transfer of email messages through the network. Devices that are used to reliably transfer the email messages through the network are called agents, and their communication is defined by the SMTP protocol. The basic communication between the SMTP client and server is presented here, and it can be seen that it starts with an introduction from a server and a client. After that, the client defines the sender and the recipient of a mail message by defining their email addresses using the commands mail from and recipient to. After the command data, the client defines the whole mail message, including the email header and the email content. After the server's response that the mail is queued for delivery, a client with a command quit requests closing the transmission channel. Proof-of-work systems emerged with the aim of preventing abuse of the processing power of a device, for example, during the denial of service attacks. The basic idea behind this concept is to request relatively small amount of processing time from a device which tries to access protected resource. This prevents the basic feature of the mentioned attacks, a large number of access attempts at a resource over a short period of time. The principle behind how a proof-of-work system works is based on a typical cryptographic scenario during which one side that takes part in the communication attempts to prove its validity to the other. Specifically, the client who is requesting a service or resource from the server should prove its reliability. So in the picture, it can be seen that after the requesting of the service from the server chooses the requirement it will send to the client. Then the client has to solve the challenge that was set by the server. Most often, the solving of the challenge includes the multiple execution of mathematic or cryptographic hash functions in order to generate a response or a solution to the challenge. So that response is sent to the server, which has to verify it. After the verification, server can grant the requested service to the client. The idea proposed in this paper is the possibility of asking a potentially unreliable SMTP client for proof of credibility by requiring certain amount of processing time each time a client wants to send an email. This algorithm represents the behavior of the server during the client-server communication. After accepting client connection and receiving the whole email header and the email content, server has the possibility to evaluate the client through the reputation system, and if the client is identified as reliable, the server can transfer the email message directly as it would be done in the basic SMTP protocol. But if the client is not reliable, the server has the possibility of requesting client processing time. After that, server has to validate the client solution it had received, and the solution represents the result of client processing time. If the solution is correct, the client is identified as reliable, and then his email message can be transferred through the network. But if the solution is not right, the SMTP server has a possibility to notify to the SMTP client about the message not being sent. After that, the connection, client-server connection is closed. Implementation of the proposed system described earlier requires certain changes in the implementation of the SMTP protocol, or to be more precise, requires certain changes in the SMTP client-server communication, as it is presented here. As it can be seen, the beginning of the server and client communication is the same as it is in basic SMTP protocol. But after receiving the whole email message, the server has a possibility to request a certain amount of processing time from a client. That is done by defining the integer value, which is called the wait parameter, and the wait parameter represents a requirement that a server would send to the client. In this specific example, that requirement is the wait parameter of 3, and the wait parameter represents that the client has to generate a sequence that has as many zeros as was defined by the wait parameter. If we consider this example, that would mean that the client has to generate a sequence that has 3 zeros in the beginning. The way for a client to generate a sequence is to execute a cryptographic hash function on the email data. It is known that the multiple executions of hash function on the same data would generate same outputs. So the client has to append a nonce value on the email message and to execute a hash function multiple times sequentially until the nonce value is the right one that will generate the sequence that has 3 zeros in the beginning. Nonce value changes with every execution of hash function. After the client has found the right nonce value that will generate the wanted sequence and would meet the requirement of the server, it sends it to the server. Server has to verify the nonce value, and after the verification, it can send email message through the network. The verification is done by a single execution of hash function, and that execution is done on the email data and the appended nonce value that the server has received. The SMTP server, which has been described, is implemented using .NET Framework. the implemented server has been tested on an AMD A10 model processor with a clock speed of 2.10 gigahertz, and the distributed spam attempt during which the server load was tested was simulated by a cluster of 10 SMTP clients. Each client used the Seagull traffic generator tool, and that tool was used to simultaneously send multiple requests to the server. Performance measurement and analysis has been done, and it was evaluated the client processing time, then the impact on the overall amount of sent spam messages, and the resource usage of an SMTP server was evaluated during the distributed spam attempt. An evaluation of the client work was evaluated through multiple testing of various weight values assigned by the server. The amount of processing time required from a client has been evaluated in that way. The results obtained are presented in Table 1. And it can be seen that with an increase in the values of the weight parameter, the amount of required CPU time increases. And we can see that it can be significant, for example, for the weight value of 4. The exact CPU time that a client has to spend on solving the requirement set from the server depends on the speed of the CPU, depends on the usage, current usage of the CPU, and also it depends on the probability function that defines the exact step when the nonce value will be found. Before we discuss the exact impact on the amount of sent spam messages in the network, we have to discuss the hash power parameter of the CPU. CPU's hash power parameter defines the number of hash function executions per second that the CPU can perform. So if we look at the figure 1, we will notice that the number of client hash function executions per second per individual request decreases from the value of CPU's hash power, and it happens with an increase in the number of simultaneously sent requests from a single client due to its CPU overload. The direct consequence of the decrease in the number of hash function executions per request is the increase in the duration of the individual client-server connection, also with an increase in the number of simultaneously sent requests. That can be seen in figure 2. And if we consider the both presented results, it is obvious that the number of possible client-sent emails per second is constant, and it does not depend on the number of requests that are sent from the client. This equation here is used for calculating the number of possible client-sent emails per second. And in the equation, HP is the hash power parameter of the CPU, the T is the weight parameter, and the H is the average number of required executions of the hash algorithm, which was presented in Table 1. For a weight value of 3, according to the equation, the number of sent client messages is calculated and is 0.345. As can be seen in figure 3, testing of the implemented server for the weight value of 3 approved the value that was obtained using the equation. During the distributed spam attempt, the client CPU usage was evaluated, and it was evaluated depending on the number of simultaneously sent requests for sending an email. The client CPU usage was evaluated while using weight value of 3, and the results are presented in figure 4. we can see that the sequential execution of hash functions overloaded the tested client CPU to 100% in the case of 30 simultaneously sent emails. And that observation was used while evaluating the email server resource usage during the distributed spam attack. To be more precise, implemented SMTP server load was tested during the distributed spam attempt, which was simulated by 10 SMTP clients, and each client used the Seagull tool to simultaneously generate and send 30 email requests. And each of the SMTP clients was their CPU usage was 100%. As it can be seen in figure 5, the CPU usage of the implemented SMTP server was not greatly affected by the distributed spam attempt, even in the case of 10 clients simultaneously sending requests. And to conclude, in this paper, we designed and evaluated an anti-spam solution based on a novel proof-of-work concept. In order to enable the evaluation using the proof-of-work algorithm, the SMTP protocol extension has been designed and presented. The implemented system has been evaluated during the distributed spam attempt, which was simulated by Seagull tool. Conclusions that are made from the performance measurement and analysis is that the client with the intention of abusing the email server is limited to a constant number of sent emails per second, and that number is irrespective of the number of requests for sending email. And that means that the speed of sending emails from a potentially spam client is limited on a constant number. The second conclusion is that the CPU usage of the implemented server was not greatly affected by the distributed spam attempt. We received a question that says, can you discuss the overall bandwidth in mail protocols when spam is concerned? And the second question was, are there ways to eradicate it on the technology levels prior to reaching consumer inboxes? So the answers are that if we consider the average email size of 75 kilobytes, that is we can find the overall global bandwidth. If we divide the 1.8 billion, which is the number of daily sent spam messages, if we divide that number with the number of seconds in the day and we multiply it by the average email size, we would generate the overall global bandwidth that is used by the spam traffic globally. If we consider the fact that 50% of email traffic is spam, approximately 50% of every global link is used of every link's bandwidth is used for the purpose of spam traffic. A proposed solution limits the number of emails that can be sent in a second to 0.345 for the weight value of 3. So if we calculate the average bandwidth that is used by a single spam client, it would be 0.345 multiplied by 75, which is the average email size. And the answer to the second question is that the proposed solution doesn't discuss what would happen if a client is identified as unreliable. There are many options, but one option certainly is to notify the SMTP client about the message not being sent, about the failure of sending email message, and to not deliver it to the consumer inbox. So that would be a way of dealing with spam messages on the technology levels prior to reaching consumer inboxes. And with that, I will conclude this presentation. Thank you all for your attention.